For our second installment of Chapter 21, Nuclear Chemistry, we're going to talk about radioactive decay and some applications of this process, such as carbon dating. A couple more terms to be familiar with in this section. Okay, we introduced the term nuclide in the first video. Okay, and radioactive decay is the spontaneous change of one radioactive or unstable nuclide into another. Okay? And in the previous video, we said that we're always spontaneously reacting to form a more stable nuclide. Might still be radioactive, but it's closer to the belt of stability. Okay? And when we're undergoing a step in a radioactive decay process, our reactant is called the parent nuclide. That's the thing that's unstable. And it undergoes decay, and there's a couple types we're going to see in this section, to form what's known as the daughter nuclide. Okay? That's what results after decay. We might stop there after one step if it's stable, or we can decay further. But we're always moving to get closer to the belt of stability and end up being something that's not radioactive. So what's that process look like? Here's the radioactive decay of uranium-238, which happens by a process known as alpha decay because it emits alpha particles. Okay? The parent is uranium-238. It emits an alpha particle, and the daughter in this case is thorium-234. And the emission of those alpha particles is something that we saw all the way at the beginning of Chem 1550 in Chapter 2 when we talked about the discovery of protons in the Rutherford gold foil experiment. Okay? Used alpha particles. Those alpha particles could be focused, right? And then used for experimental observations. We can do that with alpha particles. We can do it with beta particles. We can do it with gamma rays as well. Okay? And those would come from different types of radioactive decay. Okay? We've introduced now alpha decay, and you should know all these types of radioactive decay. Okay? Alpha decay, emission of an alpha particle, right? It decays by getting rid of an alpha particle, alpha decay. That happens with our heaviest nuclei, okay? Because we lose quite a bit in an alpha particle. Beta decay, right? The emission of a beta particle from the nucleus. And remember, we defined a beta particle previously as a high energy electron. The key thing to pay attention to with beta decay is its emission of an electron, a high energy electron, right? But it's not one of our surrounding electrons. We're actually ejecting an electron from the nucleus, which comes from a process where we have a neutron that gets converted into a proton. Okay, so we shoot an electron out of the nucleus. That's beta decay. And both alpha and beta decay change our proton to neutron ratio to move closer to the belt of stability. Remember that image from the first video. We also have gamma emission, okay, which is where a nuclide is in an excited state. We don't change the proton or neutron count, right? So we don't change the mass number, but we do lose some energy to decay to a ground state. Think about it like an excited state electron falling down in energy and emitting light. Same type of thing with gamma emission, but now we're emitting gamma radiation. And here's what a couple of those look like. Here's alpha decay on the top. Remember, we can represent an alpha particle as a helium nucleus or with the alpha symbol. Okay. In the middle there, we have beta decay, where we can represent it as the electron or as a beta particle. And on the bottom, we have gamma emission. And that asterisk next to cobalt 60 there represents the excited state. So notice we start with the excited state, finish in the ground state by emitting gamma radiation. Okay, so alpha decay, beta decay. Both of those things have an alpha particle or a beta particle respectively as a product. And then we balance the nuclear reaction like we did in the first video. What other types of decay do we have? Okay. There's something that's known as positron emission, okay, or beta decay. Okay, positron emission or beta decay. That's the emission of a positron from the nucleus. Okay. That's something for a low neutron to proton ratio, where we're below the belt of stability and we're trying to move up. Oh, sorry, I said beta decay here. Positron emission, positron decay. Right? Be careful, B plus, right? Positron, as opposed to just B. That's the beta particle. That's my bad. Okay, positron emission, positron decay. That's why we don't try and read and talk simultaneously. We also have electron capture, where one of our core inner electrons is captured by the nucleus. Okay? So it's kind of the opposite of the electron emission we talked about before. Now, the net result, okay, of positron emission and electron capture, they actually have the same overall effect. Okay? We'll see that on the next slide. The different processes, which one actually happens, depends on their different activation energies, which is unique to each radioactive nucleus. Okay? On the top, shown here is positron emission. On the top is electron capture. Notice in both of those situations, our mass number stays the same, but our atomic number decreases by 1. Okay? So we, again, affect the neutron to proton ratio now to move up closer to the belt of stability. All of those processes are summarized on this figure from your textbook, 21.7. You should be familiar with each of the 5 types of radioactive decay. So, we also, from these processes, have something that's known as the radioactive decay series. Because everything that's naturally found on Earth and radioactive falls into a couple of things that are called radioactive decay series. No matter where we start, we end up in the same place because we fall into this chain of successive decays, which ends at a stable isotope. And there are 3 of them, okay? The uranium series, the actinide series, and the thorium series, all of which end at lead, different lead isotopes. Okay? So here's the uranium series. Starts with uranium-238, okay? And then we end up falling the same way to end down at lead-206. Okay? And this is a process we can take advantage of in radioactive decay, radioactive dating. Okay? Because other things, right, they might not start all the way up at uranium-238, but they will fall down into this series and then end up at lead-206. Same idea for the actinide series. So how does this relate to radioactive dating? Okay? Radioactive decay follows first-order kinetics, okay, which we talked about in Chapter 12. All of our radioactive nuclides have a constant half-life when they decay from the parent nuclide to the daughter nuclide. So we can use the half-lives of those isotopes to determine useful information, right? How long a sample will be available, right? How long something's existed. Or if we've got radioactive material, waste, for example, how long do we have to store it until it's not harmful anymore? And this is what that looks like. Here's the decay of cobalt-60. Okay? That has a half-life of 5.3 years. And we see, right, after 5.3 years, 1 half-life, we go from 10 grams to 5 grams, and then it halves again, halves again, halves again. So we can use that to take advantage of nuclear kinetics, which follow the same kinetic principles we introduced before. These are formulas we saw in Chapter 12. Okay? So now if I substitute, instead of using concentration, I use the number of nuclei, which is represented by the capital N, right? I can calculate number of nuclear decays, just like I calculated activity before, okay, where lambda is equal to a decay constant. Just like previously, we used K as a rate constant. Okay, so rate equals lambda N. Lambda is a constant, N is the number of nuclei, okay, which gives us the 2 formulas on the left. Same exact principles from Chapter 12, just different symbols when they are radioactive. Okay? And you'll have to use that on your sapling to solve a couple of problems. But be aware that the half-lives for those nuclides can vary significantly, right? Here we see we go from 110 minutes to 73 hours for things that are used in the medical fields, right? But these things can also be tens of thousands of years, because that illustrates, again, the difference between thermodynamics and kinetics. All of these processes are thermodynamically spontaneous, right? But they kinetically vary quite a bit. Some are fast, some are slow. The most common form of radiometric dating, which is using, right, those isotopes to gather information, right, something for things that have useful half-lives, right, is radiocarbon dating or carbon dating, which uses carbon-14. Okay? Carbon-14 is unstable, radioactive. So we can use radiocarbon dating for anything that contains carbon. up to a maximum time of 30,000 years. Okay? Beyond that, then all the carbon-14 has pretty much disappeared. Okay? And the reason for that is because most of our carbon that we encounter is carbon-12. There's only trace amounts of carbon-14, about 1 part per trillion, because carbon-14 is formed in the atmosphere. When nitrogen, which is most of our atmosphere, right, 78%, reacts with neutrons, which come from cosmic rays, that forms our carbon-14, which is radioactive. Okay. And then that carbon-14 eventually decays, right? But in the meantime, when that carbon-14 is produced, any type of carbon can react with oxygen to produce CO2. Carbon-12 is most of it, but carbon-14 can do the same thing. And then when I've produced CO2, right, it can get taken up by a plant. And then if it's gotten taken up by a plant, it can also end up in things that ate the plant. So anything that contains carbon has a ratio of carbon-14 to carbon-12. You've got some carbon-14 in you right now. Yep. And the ratio of carbon-14 to carbon-12 depends on the ratio in the atmosphere. Right? But then after the plant dies, so it stops taking up CO2, or an organism dies, it stops taking up plants, then the carbon-14 starts to decay. And luckily, it's got a long half-life, right? 5,730 years. But carbon-12 doesn't decay. So if I can measure the ratio of carbon-14 to carbon-12, I can get at the information about how much time has elapsed, right? Just from that simple ratio, I can tell how much time has gone on. But then, right, after about 6 half-lives, I don't have enough carbon-14 left to detect. So that's why I max out at about 30,000 years. Okay? And those are measured via a process known as mass spectrometry. If you continue on into organic, we will discuss that. And then we finish this slide, right, just showing how that carbon-14 is produced and then brought into the carbon cycle. Okay? In our final video, we'll talk about other applications of radioactivity. From this video, make sure you're familiar with all 5 types of radioactive decay.